Alrighty. Hello everybody to this online meeting for MTH218 Multivariable Calculus. So this week I'm going to look at some revision sort of aspects. So there's lots of things in this subject. So I've been asking people what they want to do, and so these are some of the things that people have asked for essentially that I'm going to look at. So I'm just going to work backwards essentially in the main. So assignment 3 is almost due, so I just want to talk a bit about how to use Maple to help with some of that aspect. Talk a bit about the exam in general, then just work backwards to some of the key ideas that we've seen in the subject, so flux, line, and double integrals in particular. I might not get through all of them today. That's okay. I'll roll over some things till next week. But the things that are most relevant to assignment 3 and assignment 4, I'll do today in order to help out. So, firstly, assignment 3, which is almost due. So, the intention very much is to do all these things on a piece of paper, but you might want to check your answer. And so one way of checking your answer is to use Maple to help you out. There's other programs like Wolfram Alpha, which is a web-based program which can help with the integrals directly. But Maple can help with lots of the vector calculus. And so here are some commands which you can do. So I'll try to do this quickly, essentially. Make it slightly bigger. So there's different types of line integrals. Is certainly question 1 of assignment 3. So just mention the Maple for that. So if you're doing a scalar line integral, so an integral of FDS, for example, then in Maple they're called path int. So P-A-T-H capital I-N-T. And it's case sensitive. You have to write exactly in that sort of format. In order to use them, you need to insert a package called vector calculus. So you start with vector calculus, capital V, capital C. If you want to, these notes I will put up on the Interact 2 site later, and I can put all the raw commands in as well if you wanted to, but that's the main thing. So it's path int, then it's the int what you're integrating, then the variables, so x and y, is equal to some sort of domain, is what really is required. So in the most general situation is you have a path, so capital P path, then in angle brackets, the parameterization for the curve and the parameter. You can do it over 2 or 3D, so this one's a 2D version, but you can put another comma HT for the Z if you had 3 variables, etc. So that's what it is in general. So if you just do it as written like that, then that will give you a number. So it just gives you a single number. If you put a comma inert at the end of it, then it will give you the integral that Maple evaluates in order to get that number. And so using both of them is a useful way of checking your answer. So the inert version would say, well, have I managed to reduce this problem down to the same sort of integral that Maple's doing? And the top one would go, is Maple getting the same answer that I'm getting? And now you can type things into Maple incorrectly, of course, so it may be Maple's problem rather than yours, but or handwork. But it's a good way of checking your answer in 2 different stages. So I've listed at the top just how you do it in general. This is more an actual example for 3D, which I've written down here. So this is a path integral. So this would be the integral of x ds essentially along a path with this parameterization where x equals t, where y equals t squared and z is equal to 2t cubed on 3, if you can read that. Now, when I give the PDF for it, if you want to copy and paste, just highlight a whole thing and copy and paste into Maple, just one thing of warning is that when copying from a PDF, the hat symbol, that little hat symbol, doesn't copy across properly into Maple, and same thing with quotation marks. So quotation marks often don't copy across properly. That's of the typesetting used by the PDF document, which regrettably I don't have control over. it changes the character along the way to make it look better as far as it's concerned, but it means it doesn't copy across properly. And so if you are copying and pasting these, you got to make sure you change the character, just retype them in yourself. Just with any of these things, although you can use general paths, you can do any sort. There is some special paths that it also knows, like straight lines or line segments, circle or bits of circles. So there's sort of 4 different cases listed there, and they might be useful. And so you can do a whole zigzag using this line segments option. Now, if you want any, so okay, if you're going, well, if that perks your interest, I can explain into a bit more detail. But that's just the basic sort of formats that you can utilize. Now, the other sort of one you might want to look at are vector line integrals. And again, you've got to include the package with vector calculus. Now, these are integrating over vector fields. And so with a vector field, it's important to talk about what coordinate system you're using, just so it knows what derivatives to take, etc. So if you think about it, it's integral of f dot dx. So the dx here, really, you need to know, in order to integrate with respect to this dx, you need to know what the variables are. So in order to do that, you need to tell Maple what the coordinate system is. And the way to do that is use the set coordinates. We often use Cartesian and either x, y, or variables x, y, z. And that just works out what the dx part means in the integral, essentially. Otherwise, you're doing a line integral, but you need to tell it, and the integrand is a vector field, and so in general, you need to top in the word vector field and then open brackets, then top the vector field. So here's an example down the bottom of a vector field where the components are z, x, and y, for example. And then just like we do for the other case, you just give a domain, which can be a path or one of the special cases like line segments or circle or whatever it might be. And if it's in 3D, you just have to remember that a third component. So these are your things useful to check. And like above, you can put the comma inert if you wanted to give an integral rather than just a single number. So if you want to, you can use these to check your answer. The last things that are accessible in assignment 3 that you might want to check in Maple is curl and divergence, which someone asked today as well. So again, you need to do the with vector calculus, and again, you need to use set coordinates to tell it what coordinate system to do it in. So the formula that gets used depends upon the coordinate system. So the formulas that we've for curl and divergence always resort to Cartesian x, y, z. That's what we're doing it in. And then you just do curl vector field, whatever it might be. So let's just try to do an example. I've got to make this as big as I possibly can. So if you do with vector calculus, then you do want to set coordinates, and it's Cartesian x, y, z. That just gets the coordinate system right for us, and we can do things like curl of a vector field, something like say 0 x squared plus x 0. So that would be the curl of basically no i's, x squared plus x times j, and no k's. What did I do wrong? Okay. And put in an angle brackets. There you go. Make this answer a bit bigger. So you can see the answer is 2x plus 1, and it's got e bar z. That's another way of saying, well, it's what we write as k down. So e bar x would be I, e bar y would be j, for example. So that would be the curl is 1. And you can do the same sort of thing for divergence. So you just copy, paste it, type in divergence. And now the divergence in this case is 0. Now, in your assignment, you need to make sure you show working as well. So showing how you get it all. So this maple, particularly for the curl one, skips quite a few steps as it does to divergence here. And so you need to know exactly how it is. So that might help addresses what someone's question is today, just how you can do some of these things in maple. Okay. So that's the assignment 3, so things most pressing. So now, since we are talking about revision, just want to talk a bit about the exam. So there is a section in the study guide about the exam, which talks about it a bit at length, and in the Interact 2 site as well, there is, under the assessment items, there's just a few of the key links, including a few statements. So there's lots of information there. Please read it. It's much more detailed than what I'm writing down here. But key idea is there's 6 questions, and each question is a group of things, really. Just like it is, in your assignments for that matter. It's 3 hours and 10 minutes. So the intention is that 10 minutes is reading time and 3 hours writing time, although it's a bit fluid now that you can write in your reading time, so to speak. So it's a 3 hours and 10 minutes exam. But I'd encourage you to read through the exam first and look for the questions and again, you can pull out a pencil and flag the ones that are easier or harder for you, and you might want to do the easier questions first. There are roughly 2 questions per chapter. It's not precisely like that. I have a slight bias towards the latter chapters, so chapter 3 and 2 in particular, but it's still roughly that case, and it's roughly in order of the subject too. So people probably find the early questions easier, but I mean, it's up to you. You can tell me afterwards if that's true or not, because so difficulty is really dictated by the people doing it, which are yourselves. It's technically a closed book exam, which means you can't take any old textbook you want to in, but you are allowed a double A4-sided piece of paper with anything wanted on it all, so it can be typed or handwritten or both, and so it's basically a formal sheet sort of allowed. So you can prepare your own for all intents and purposes. So I've produced an example one, which if you can read it from where you are, well done. So this is an example one. You can see in a few places. It's linked to the beginner study guide. It's in a few places on the Interact 2 sites too. So if I zoom in a bit, got a better chance of seeing it. So I've just written down lots of formulas that I think are a good way of summarising the subject. Some of them may not be that useful in an exam situation, admittedly. I really have tried to write it down as a summary for the whole subject as a whole. And so things like a 2D Taylor series, for example, it was mentioned in part of the notes, but you're not going to be assessed on that as an example. But there's lots of things which are useful. It's written in a format which I find okay. You may not. So it's only my formula sheet as such. I filled it up with lots of stuff too. There is a bit of blank space over here, but what you might want to do is you might want to produce your own. And so you might want to print it out, cut out bits you don't like, and erase some blank space and write a few worked examples down. Or you might want to annotate some of this. You go, look, well, most of this is all right, but I just don't really think of it. I don't really like some of the fact I use some of the gradient notation all over the place at various points of time. You might want to scratch it out and explain it in words that you'll understand better. That's fine, of course. But you've got to make sure that whatever form sheet you bring in, whether it's a whole brand new one or whether it's this with annotations, that you can utilize. So, what sort of formula sheet what are you thinking of doing for a formula sheet? So the few people that are on today, What's your plans for your formula sheet? Have you thought about that? Just want people to think about the answer. Yep, so putting some examples down sounds a good idea. So you can do, you can make it as small as you want to. I have seen people where they've reduced it down substantially. If you want to, that's fine by me. I mean, certainly people make works of art of these sort of things. So worked examples, a good idea. You can see my example, and I've put a few pictures in and a few formulas. So you need to start thinking about it and make sure that you can use it in the exam for your benefit. In addition to the formula sheet, which is a good thing to get ready, there's a sample exam, which I'll do one or two questions from. I'll allude to a few questions as going through today. I'll mostly leave you to do them. So the sample exam gives you an idea of the structure of the exam, sort of how it's laid out. So that's the 6 questions idea. Your exam is different. They're not, so it's not just numbers swapped around or anything. It is a bit different. So so be prepared for a bit of variety. So it's really trying to show the structure and sorts of questions you might get in there. In addition to that, there's some revision questions, so which is a bit like a second sample exam, so to speak. And both of them have solutions available. The sample exam have video solutions for all of it as well. So utilize those as for your revision purposes. Next thing is I want to talk about some revision. So let's look at some of the key aspects. So the last main thing we looked at is the idea of flux integrals. And you haven't been assessed on that primarily yet. So that will be assessed in the exam in a big way and in a small way through assignment 4. Okay, so I guess a good way of thinking about it is what strategies. So I'm looking at, with flux integrals, as you've seen, I'm sure if you've been doing some examples, each problem, there's more than one way of doing it. What is the best way of doing it? The best way probably is the way you can do. But this is my list of strategy. This is the way I would try to tackle them in my order of thinking too. Now, I'm certainly biased towards a high-level theorem, so I certainly like Stokes and divergence theorem and Green's and things like that. So I would do those as much as I possibly could. You may not like them, so you've got to work out your own preferences, but just mentioning it. So the first thing I do for a flux integral, so flux integrals look like this sort of thing. I would, if the surface is closed, that's the first thing I look for. I'll just check if the surface is closed. So a surface is closed means it has no boundary. And if that's the case, then I'd use divergence theorem. And this is an example question is working a flux over a sphere. So a sphere has no boundary. So as soon as I see that, I go, well, bang, I'll give it a shot of trying divergence theorem. I won't do all these examples, but just showing you where some of them might look for. Next thing is, if I'm doing a flux integral like this one here, where the integrand, or the vector field, has got a curl in it, so it's actually a curl, then I would consider using Stokes' theorem. So Stokes' theorem very much has that sort of format. So if you're going to flux integral of curl of something, then thinking, well, Stokes' theorem might be a good way of doing it, and Stokes' theorem would convert that into a line integral. Now, in practice, the way to do that line integral might often be using Stokes' theorem a second time, and so an advanced technique, putting it all together, if you've got two different surfaces, so S1 and S2, for example, which have the same boundary, so both of them have the same boundary, and the orientations match up, then the flux integral of the curl over one surface is the same integral over the different surfaces. So the integral of both surfaces would be exactly the same. So this is some generalization of path independence. So this is sort of like surface independence sort of thing of this sort of vector field. So if a vector field has zero divergence, then it's surface independent. So I guess the sort of idea. Now, so that's double Stokes theorem essentially. And I said you'd only use that if you're doing a double integral of curl, and it's just a way of doing it. So where is it useful? That's really useful if the first surface, like this paraboloid in the example here, is complicated, but you can find another surface, like in this case, like a circular disc, which is much easier to integrate over. Say, for example, one that's in a plane. So that would be where the benefit comes from. If you're doing Stokes theorem twice, the second application, if it's sitting in a plane, so simply sitting in the xy plane, then that really can be thought of as being Green's theorem. But they're the same. So Green's theorem is just a special case of Stokes, so it's really just a special application for it. So that's the advanced technique. But just going back, closed surface, divergence. If you go curl it, vector fields of curl, try Stokes, and then see what happens after that. Otherwise, you're going, then the standard approach is really just to try to just tackle the problem more directly. And so the direct approach would be to write double integral of f dot ds as really f dot n, where little n here is the normal. Now, if the unit normal is easy to work out from a geometric point of view, then do that. So that applies nicely to planes. So you've got a plane, then the unit normal is pretty easy to work out for a plane, because you know that from Maths 102. Or if it's a sphere, again, it's just sticking outwards. They're easy to work out. So sometimes you can use geometry to work out little n. And if you do that, then you might be able to integrate pretty quickly. And so an example of that would be if you're doing a flux integral over a rectangle, then a rectangle sits in a plane. And so if you look at those ones, that would be the plane z equals 1. And I didn't mention the orientation, but yeah, so as soon as you know that the rectangle z equals 1, that means that the normal is going to be k or minus k, depending on the orientation, and that allows you to process the rest of the problem. So that's using the geometry. So again, some surfaces lead you to that. So what happens if all those fails? Then there's sort of two options that I would consider. One is the advanced technique, which I mentioned first, and the other one is just parameterization. So the advanced technique, and again, don't feel you have to do this, but I find it useful at times, and this shows you my bias to liking the high-level theorems, is if it's an open surface, then just close it off. So close off the surface, and as soon as it's closed, then I can use divergence theorem. So let's just use make a bit of a picture, show you what I mean. So say I've got an integral over a hemisphere, something like that. So the surface is really just this top part here. And you can see that it has a boundary on it right at the bottom here. So the boundary is a circle. And so this is an open surface. So if I'm trying to do a flux integral over this, well, it's open. I can't use divergence or anything like that. But if I closed it off by putting another thing in the bottom, so if H is on the top and I close it off by putting a little disc on the bottom, if I make sure the orientations match up, so if the orientations are both outward facing, or is the key way of using divergence theorem, then what I can do then is the flux integral over H plus the flux over the disk would be the total flux of this entire surface, would be then equal to, via divergence theorem, the triple integral over the solid, let's call it V, and that's divergence theorem. So divergence So writing things for short. And so therefore to work out the flux integral over the hemisphere would be the triple integral of the divergence minus the flux integral to the bottom. That's how I've written it down the bottom here. So the flux through a surface is triple integral over the solid minus the flux through the bottom. Now that only really works if these other two integrals are easier to do. And so I would only do that if the surface I'm closing things off with is much easier than the surface I had to begin with. So I'm not making it more complicated. It's an advanced technique. It sometimes works really helpfully. It's sometimes really helpful. But up to you. So again, I would look for, that's not the first thing to look for. So if nothing of this works, then what you really are forced down to do is to parameterize. So the easiest parameterization is just using Cartesian coordinates. So just parameterize using x and y. If it's on the side, then maybe y and z or etc. But really just parameterize in terms of x and y is by far the easiest to do. When you parameterize it, then you only have to work at this thing called capital N, and this is what results from whenever you parameterize. And this is the sort of formula for capital N just here. That's on the formula sheet. In terms of x and y, if you've got parameters x and y, then it's a straightforward formula. It can be plus or minus. It can be upwards or pointing up or down, so to speak. And you have to look at the orientation required to work which if it's plus or minus. That's a key part and difficulty, for that matter, of working this sort of problem type out. Utilizing what the normal should look like in the k direction is often how I'd resolve it. And when you've got this capital N, then the ds part of it is this capital N dx dy. And if you've just got a surface integral, it's the norm of the length of n dx dy, and that's that sort of formula there. I'll do an example in a second from assignment, the optional part of assignment 3. Now, this is parameters for Cartesian coordinates, but even for other y cases, so even if you're looking at like something like a circle, where you think polar coordinates would be the way to go, or even if it's ellipse, which is something else, some other sort of elliptical coordinates or anything like that, then normally it's still easiest to parameterize in terms of x and y's because the formulas are straightforward. And what you end up doing is, once you apply this case, you get dx dy. Your next step would be then to substitute into polar coordinates. So do it as a gradual step process. So in general, you can parameterize any parameters you want to at all. It doesn't have to be Cartesian coordinates. And you can do r and theta here, for example. But as you notice, the formula gets a bit more complicated. So you have to work out the partial derivative of the x, y, z with respect to both parameters, take the cross product of those two, have to think carefully about which direction it is to work at capital N, and then the same sort of formulas approach. So although you can do this to work at polar coordinates, things like that directly, I certainly think in most practical cases that we're going to do with doing Cartesian coordinates first and the second one afterwards would normally be well and truly sufficient. The only example I really did for this is, say, spherical coordinates I've done once in the notes, etc. So I showed you it in general, but I think Cartesian normally is the way to go. Okay, so that's enough for me talking about theory. Let's just try putting some of these in practice. Just trying to think what it is. So these are all questions from assignment 3, the optional part. So it's good to try them yourself, and I will provide answers for them when it comes to it. But just talk about the basic strategy behind it, and we'll do some of them. Okay. So we've got to think about what strategy to apply here. So first of all, I know it's a flux integral. So it's a double integral of a vector field dot producted with the norm of the surface, essentially. So it's a flux integral. So flux integrals, first thing I'm thinking of is, well, is it a closed surface? That's the first thing I check for. And what do you reckon? Is it closed or not? You have to read the question immediately to work that out. What do you guys reckon? Is it closed? If you don't know, just put a question mark. It's fine. Okay. So because it's a whole rectangular box, so it's a rectangular prism, so just the outside of the box, then it means it has all 6 sides of the rectangular prism, so it is indeed a closed surface. So as soon as it's closed, I'm thinking, well, let's just try divergence theorem. So for divergence theorem, this would be the triple integral of the divergence of f integrating over the entire volume. So because it's closed, that's the key idea. So you have to work at the divergence. So that our divergence would be, if you look, 6. So I'm just skipping some steps. So this would be the triple integral of 6 dv. Now, integrating over boxes is not difficult, but you can do a trick here. You can factorize the 6 out, and so it's 6 times the triple integral dv, which is just, and whenever you time integrating 1 dv, that just ends up being the volume. And so you work at the volume of the box. So the volume of the box, the length times the breadth times by the height would give you the answer. So the answer is going to be 24 in the end, using divergence theorem. So 2 things I want to mention there is, the first, recognize it's closed, therefore divergence theorem. And next is, when you're doing the triple integral, look for tricks. You can utilize, oh bang, that's just an area or just a volume, and use the geometric properties to help you out where necessary. So you look for those things because it saves a bit of work. This was integrating over a box like this isn't very difficult. So I could have done this integral directly with not too much fuss either, for that matter. It isn't that hard, but using the volume is helpful. Okay, where's my cursor gone? So let's do this one. So again, as soon as you say it's a flux integral, so you know, okay, first thing, is it a closed surface? Do we have a closed surface in this case? What do you guys reckon? Is this one closed? And the answer is no, that's right. So it's just a, so if I draw my picture, it's a elliptic paraboloid even, looking something like this. So it's only the top part of the surface. So it's got a very clear boundary to it, which would be some sort of circle in through it in the XY plane. So it's not closed, so that doesn't work. Next thing is the vector field a curl? And well, it doesn't look like it from the, you can't, it isn't obviously so, and it's a bit harder. And at first glance, if you look at this, you go, well, it doesn't look like a curl at first glance either, for that matter. So it does, it's not one of those. So you can't, not really going to apply Stokes' theorem either. So divergence and Stokes' theorem, the direct approaches aren't going to work. So what you really are resorted down to is, well, is it a nice, so maybe if it's a really nice geometric object, I can work out little n, the unit normal, quite easily and go from there. And the answer is, well, it's a paraboloid. That's not such a neat geometric object. I don't know what the unit normal of that is off the top of my head. So that one doesn't really apply either. So what you really are left down to doing then is really resorting down to parameterizing. That's one option. Or the second is to try to use that in my advanced technique of the sneaky way of using divergence theorem. Now, I'll do them both. Which one would you think to do? So if you were trying to tackle it, which one would you try to do? And that's one I'll do first. But I'll show them both to you. And then I think the answer is whatever you think to do first would probably be the best option. But you can see how you eliminate all the other ones. Any preferences, what people want to do? So this is called, I'll do the parameterization method first because no one suggested anything otherwise. So this is what I would think has been the direct, most straightforward approach. Certainly when I've talked to students in the past, some students don't like this method. It's sometimes feel a bit too complicated, and using the high-level theorems is they prefer. Other students the other way around. So it really is up to you. So the parameter approach really just means we need to parameterize the surface. So basically, you need to make the surface a function of x and y. It already is. So that's fine. That's done already for us. We don't have to worry about it. Then we have to find this normal thing, this capital N normal, and copying the formula from my formula sheet. It's the partial derivative of z with respect to x, the minus sign, minus the partial derivative of z with respect to y, and then 1. And again, it can plus or minus depending on the orientation. So we have to be more careful of that. So if you look back at our surface at the top here, we just got to take the partial derivative of this thing here with respect to z, of respect to x, I should say. So part of this will give you minus 2x, minus minus will give you positive 2x in this case. In a similar way, the partial derivative with respect to y is minus 2y, double negative, make it a positive 2y. We got 1. Now you have to work out which is a plus or minus, which of the two of the cases it is. Now we want it orientated upwards, which basically means the normal should be pointing up. So if you look at the y component, that's the one I always look at, then we want it, since we want it pointing up, that should be a positive number. So therefore the case that we want, or the two alternatives, is the positive version of it. So now we've got our capital N there. And then the ds part of it will now be equal to capital N dx dy, or dy dx, whatever form we want. So therefore f dot ds, which is what we're trying to integrate, will therefore be f dot n dx dy. So what we need to do then is we just need to take the dot product of f and n. So this is f just here. So we take the dot product of these two things here. So we're getting x times 2x gives you 2x squared, y and 2y gives you 2y squared, and z and 1 gives you z. And so therefore our flux integral now becomes the integral of 2x squared plus 2y squared plus z dx y, and it's a double integral. Now we just have to think about, we have to be more careful, what's the region we have here? And again, in this case, we parameterize in x and y. So really, the variables that we need to look at would be the shadow here. So the shadow of the object, or the base, effectively, of this underneath it, is really what we're going to have to integrate over. And if we look at over that, we'll call that region D, say, which is just a circle. So it's going to be so x squared plus y squared. And if you think about when z equals 0, you're getting x squared plus y squared equals 4. So the boundary would be equal to 4, and the interior would be less than or equal to 4. So I'm integrating over this disk of this particular integral. Now I won't do the whole thing for you, but just some things we need to do. So because it's a disk, we should use polar coordinate. That's a key thing. But before we do that, we're integrating with respect to x and y here, but we've got a z in the middle of it. So I'm going to have to replace that z there by x and y's, which isn't too bad because we have that available to us. So just copy that down. So just write z as 4 minus x squared minus y squared. So plug that in, which makes things a bit easier for that matter, and then use polar coordinates. Pardon me. So there's more work to do, but as you can see, this idea of parameterization converts a flux integral into a double integral. And with any double integrals, then you have to use normal approaches. And so one approach for a double integral is to draw the region of integration. So draw this disc, oh bang, that's a circle. Therefore I should use polar coordinates. As you can see, lots of these things are linked together. And you proceed from there. So that's one option. So this is the second way. So this is the advanced technique. So we've got our paraboloid, that's our P on the top. One option is, again, have a D on the bottom, but we're just going to put this is a disk that we're going to insert on the bottom. So D here is the x squared plus y squared less than or equal to 4. But because we're thinking of it being in 3D, we also think about the z component, so z equals 0. Now, if we orientate things carefully, so if you orientate the top out, if we always orientate it outward facing, then we can apply divergence theorem. And so divergence theorem, so this is definitely an advanced method, is this double integral over the paraboloid would be the triple integral of the divergence of f dv minus the double integral, the flux integral I should say, through the bottom surface. That really is an application. That's a advanced application of divergence. So if you want to think of how you want to do these, let's just talk about how you do the various parts. So the first one, you do the divergence, you end up getting 3. And so you might be tempted to pull the 3 out and go, oh, that's just 3 times the volume of the paraboloid. Unfortunately, it's not a nice geometric object. I'm not sure if you know what the volume of a paraboloid actually is. And you're going to have to do that directly. And so if you think about it, I'll just put the 3 out. So the inner integral, if you're integrating dz, dx, dy sort of thing, 1. Then the integral, the bottom surface here is z equals 0, and the top one is z is equal to 4 minus x squared minus y squared. So when you've done this double integral here, you end up getting 4 minus x squared minus y squared dx dy. And then once you've integrating that, then you're getting the shadow again. So the x and y part would be integrating over the shadow, just like that previous problem really was. And so when you've got a double integral, when the region is a circle, like it is here, then you use polar coordinates to finish off the problem. So you can see when you look comparing the two problems, both of them required polar coordinates, because they're both circular at the heart of it, to do an integral similar to this. On the other hand, things we haven't, but this problem we need to do, not just do the triple integral, we also need to do the flux over here as well. So the flux. So for this flux through D, you're going, well, the reason why I've chosen this one is because this is in a plane, and so the unit normal is easy to work out by that geometry. So we still have to parameterize it because it's still not a curl and still not closed, but at least we can use geometry to help us out a lot. So n equals minus k. And so this we can think of as being f dot n integrating over the surface area, and because it's in a plane, that's going to be really nice for us. So f dot n would be, well, just the z value times by minus 1 ds. Now, for this whole disk here, z is 0. So that's just going to be 0. So again, just like I did before, I had to sub in z is equal to whatever it was for that surface. I'll do the same thing here, z equals 0, and it comes out really nicely. So at least the second flux integral is very straightforward to do. And all the hard work really isn't working at the triple integral. So they're your two choices. They're probably not that different in the end in terms of actual work you have to require to do. They're still the heart of it really is the hard yards really are involved in doing a double integral using polar coordinates. That's where the hard work is going to be, and it's similar in both cases. What about you guys? Which way would you prefer to do it? If you had the same sort of problem in an exam, would you have done way 1 or way 2? Now, it's easy to see hindsight when you can see them both in front of you. Okay. Yeah. Okay. So everyone here decided to go way 1. That's fine. So again, you need to work out what you prefer, and therefore work out your own strategy. And in this case, I don't think it saved much by doing the more fancy advanced method. Really. So it swings and roundabouts really, but it's good to think through the various options. Okay. So this is the one's the assignment. The practice one. So this is a flux integral of a curl dot ds. So again, the first thing I look for is it a closed surface? And if it's closed, then using divergence theorems is better, even for one of the curl in here. So I still actually check for closed first. And the answer is it's not. It's a hemisphere, which is an open surface. So you can't use divergence theorem. So therefore, since I can't use divergence theorem, next question is, does it have a curl in it? And the answer is absolutely. And therefore, Stokes' theorem is the way to go. So if I apply Stokes' theorem once, then this will convert it into a line integral around the boundary. So let's just draw my picture. That's my sort of hemisphere. Now, it's good to work out what the boundary is here. So that's my hemisphere. If I set z equals 0, I can see my boundary curve here is x squared plus y squared is equal to 9. So by Stokes' theorem, which really jumps out to me as what I should try to do to simplify it, I can see the flux here is going to be the single line integral around this curve, let's call it C, say, of my vector field dot dx or dr. So it just ends up being a line integral around a circle. Now, and that's okay. You could do this a variety of methods. So it's just another line. It's just now a line integral. You have to think about how you do line integrals. So you can do it directly, and which is easier than it looks at first glance, or you can do it other sorts of ways. So let's just pause for a moment and we'll come back to that. So we have a line integral. What's our strategy to work out line integrals? How do you try to do those things? So this is my suggestion. And again, you've got to adapt it to how you feel more comfortable with it. So if you've got a vector line integral that is around a closed loop, then I would try using Stokes' theorem in a 3D case or Green's theorem if it's a 2D case. That's the way I would normally do them. Again, I certainly have a bias towards these high-level theorems. If you know the vector field is conservative, then using the fundamental theorem of line integrals is really helpful. And you check it as conservative by working in if the curl is 0. In general, in a 2D situation, it's a bit easier than that. Just show that the opposite partial derivatives are equal to each other. It's the same thing. So if neither of those two special cases apply, again, try to use geometry to help you out. So maybe you're trying to work out the length of a straight line or a circle or something like that. Those sort of things, you go, well, that makes it easier for you. So use geometry where you can. Otherwise, parameterization, which, if it's a scalar line integral, maybe that's the only real option. And so you just have to parameterize it, and it really just becomes integration by substitution that way. You can do fancy stuff like I did a second ago, and that is if you've got an open loop, you can close it off and then use Green/Stokes theorem on it. And so, again, that's a fancier one. Given how I've went before, probably won't like it. That's okay. But you don't need to use that advanced. I mean, I use the word advanced to suggest that it's not actually required in the subject. So if you're back to this situation here, think of our line integrals. We're trying to work out the line integral around a circle, which is just sitting in the xy plane. So really, for all intents and purposes, you can almost think of it as being a 2D sort of scenario. Which will make things heaps easier. So if you want to put it down, so f when z equals 0, which is in this xy plane, really just becomes, 2y cos of 0 is 1, so just 2y, I. edx sine of 0 would be 0. Plus x either y, k. So part of this some of the annoying parts of this vector field are at least a little bit nicer when z equals 0. Secondly, this differential here bit, which is the dxi plus dyj plus dzk, that's what the differentials are. If we know that z equals 0, then this thing here is going to be 0. Because if z's always 0, then it's not going to change at all. It's just going to be a constant. And so f dot dx for this particular case then is going to be in it being 2y dx plus no dy's plus no dz's. So our line integral simplifies down to this case here, which is much better, as you can appreciate. So sometimes it's good just to think exactly what we really do have at this point in time. How would you do this particular line integral? Now, it's a closed curve, so my bias would be to use Stokes or Green's theorem. And since we really just have reduced it down to just x and y's only, you'd use Green's theorem. So I would do Green's. And if you want to apply Green's on this directly, then Green's theorem is a double integral over the enclosed region, which we'll call a D for a disk and it'd be the partial derivative of the whatever's in front of the dy with respect to x, there's none of them, and the partial derivative in front of the whatever's in front of the dx by x, so it gives you qx minus py dA. So stop me if I don't understand anything, of course. So qx is nothing, py is 2, so you're getting minus 2 dA. And like my normal trick, because this is just a constant dA, then I can say that's minus 2 times by the area. And since it's a circle, at least I know what the formula for a circle is. It's a circle of radius 3, so the area is going to be 9 pi. So I did it right, which I can make mistakes like everyone else can. Be minus 18 pi. So what I've done here is I did just use Stokes' theorem once, and then what I tried to do was I just dealt with it as it came to it. So this was a line integral. I just tried to simplify it down to what I knew about it at least. And once I reduced it down, I go, oh, one sec, that's just a closed one. I might as well use Green's theorem. And you can do other options. So that's probably the easiest way in this case. If you didn't realize all those things, when I would do this one, so I'd still go, Stokes' theorem gives me a line integral. When I got a line integral around a closed curve in 3D, the default choice normally is to think of Stokes' theorem. And so you do Stokes' theorem to say this is equal to, this way too. This would be the double integral of the curl of f dot ds over my bottom bit, the bottom surface D. And that would be the curls theorem. But because D is really nice, it's just a nice plane, you can use geometry to help you out this flux integral. Was it D? Yes, yep. Because it's really nice, this N here would have a really predictable normal, and the orientation would be the same. So N here would just be K. And so it would be just the K component of the curl of F. And you work out, so instead of working the whole of curl, you have to work out the K component, which would just be based on these two terms here, and go from there. And then you do the normal thing of subbing z equals 0, etc. Now I can do the rest of the workout if you want me to, but trying to talk a bit bigger picture here, and that's another way of approaching it. So the first approach probably was easier because I simplified as much as I could before I did anything else. But you can do other things if you wanted to. So it's whatever you think of first. But again, my chief advice for these sort of things, you've got a flux integral with curl in it, just use Stokes' theorem once, and then look what you've got and think, well, how's the best way of tackling this in general? Now, it might be using Stokes / Green's a second time, but sometimes it's useful, but it's good to see what you really have there so you can make a bit more informed decision where possible. Now, you can see these things can blow out in complexity quite quickly if you're not careful. So in your exam situation, I've tried to do situations where you can work in it no matter which approach you take. Certainly some approaches might be easier than others, and I've tried to at least make so that one of the methods is not too involved. And I've tried to give some hints as well in your final exam. So you can tell me afterwards if they were of any use or not, or if you noticed that they really were hints. But yeah, so you can certainly expect some flux integrals in your final exam, and line integrals for that matter as well. So I've got more here. So that was the I've got some more things on line integrals. How about I'll leave that till next week? It's sometimes hard to swallow more than an hour of maths one go. So I'll do some more of that next week. I do have 2 weeks of revision. But if you've got any other burning questions, fire away right now. So if you want any clarifications on all those things. So what I've done today is talked about Maple. I'll put up this document on the Interact2 site in the next few minutes. So you can copy and paste stuff from Maple if you wanted to, if that's helpful. So other than that, I talked a bit, just a quick overview of the exam. Just encourage you to get the formal sheet ready, and then just talked about strategies for doing both flux integrals and line integrals, and just work through some flux integral examples. And why I did those ones because they would be immediately helpful when doing assignment 4 pretty soon. Now, if you've got any other questions, fire away. Like if you want me to copy and paste some of the Maple code into the chat box so you can use it quicker than that, that's fine by me. But anything else? So last thing is, if you can't think of anything right now, but you have other questions, then just email me during the week and I can incorporate that sort of feedback into next week's online class. Yep. So thanks very much for coming, guys.